What's up, music nerds? Today I'm reading Chapter 6 of Hermann Helmholtz on the sensations of tone. As always, the link to the webbook that I'm reading from is in the description below. You can find the entire text of the book there, as well as all of the apps that I'm going to show you in this video, so let's get to it. Chapter 6, on the apprehension of qualities of tone. Last chapter, we were looking at the number and loudness of different partial tones and how that affects quality of tone. And this chapter, we're going to find out if that's actually how our ear perceives it. And Helmholtz is going to prove it by using phase difference. So these two curves C and D are composites of these same two simple pendular vibrations, A and B. C is if they're lined up just how they're pictured, and D is if their phase is slightly offset so that this E point is lined up with D1. So if it's true that the difference in quality of tone is solely due to the relative force of partial tones, then C and D should sound exactly the same to us. Helmholtz is going to use this contraption to run his experiments. This is a resonating chamber which is on some kind of track, so it can move closer and further away from this tuning fork here, which is connected to an electromagnet, which is giving it an intermittent current using this contraption, which involves another tuning fork and a pot of mercury. And if you want to make one at home, then I encourage you to check out the appendix. But for the rest of us, he's got a set of these tuned to the harmonic series, and by moving the resonator closer or further away from the tuning fork, he can very precisely determine which upper partials are sounding at which forces. And he's going to use that to recreate different qualities of tone. He starts with the vowel qualities of tone. Let's take a look at the virtual version of this experiment. We start by deciding how many harmonics. He starts with 8 tuning forks, so let's start with 8. Then comes the fun part. We get to record a vowel sound. Ooh. All right, we can see it's mostly prime tone for that ooh. Now if I click play vowel, it's going to simulate that vowel sound by using these relative partials. Let's try oh. All right, different spectrum of partials here. Ah. Now he had to get another set of tuning forks to get to the second series of vowels, so let's add some more. E. Here's another kind of version of that experiment. We have recordings of these vowel sounds. And if we click on one of these, it'll be as if we're putting that resonator to our ear. So we're mostly hearing that partial tone. Now, if we take a look at this figure again, you'll see that there's a little kind of lid over the opening here. So instead of moving the resonator further away from the tuning fork to make the sound quieter, he can also close the aperture to make the sound quieter. And not only does that change the volume, it also changes the phase. So far as the quality of tone was concerned, I found that it was entirely indifferent whether I weakened the separate partial tones by shading the mouths of their resonating chambers or by moving the chamber itself to a sufficient distance from the fork. The quality of the musical portion of a compound tone depends solely on the number and relative strength of its partial, simple tones, and in no respect on their differences of phase. Now, we know that closing the opening to the resonating chamber alters the phase theoretically, but Helmholtz wants to show us physically by putting a tuning fork under a vibration microscope. He describes these more thoroughly last chapter, so check that out if you missed it. If we bring the fork into the most perfect possible unison with the interrupting fork and then alter their tuning a little by putting on or removing pieces of wax, we can see one figure of the microscope image gradually passing into another. We can see that in action here. Now, at this point in the chapter, Helmholtz goes into a very detailed description of how the ear works. Basically, the gist of it is the sound wave hits the eardrum here. The eardrum then sets into motion these tiny little bones, the hammer, the anvil, and the stirrup, which amplify the wave, and send it on to the cochlea, which is filled with fluid, and the fluid vibrates these little hairy filaments, which then irritate the nerve fibers. Now, how do we know that these are vibrating sympathetically? Well, you might remember that things like tuning forks, which sound for a long time after being hit, require a pretty exact pitch to be set into sympathetic vibration, whereas a thin string, which dampens pretty quickly after being plucked, can be set into sympathetic vibration by a wider range of pitches. This app can demonstrate that. The middle spring here is tuned to middle C. So if I play the middle C, now if I stop playing that, it's going to keep going for a while. Each of the springs next to it are a quarter tone higher or lower. So this spring up here should be set into motion by C sharp. And of course, these other springs are being set into motion by that C sharp, but none quite so much as this second to the top. Now, if this was a model of our ear, then we wouldn't be able to hear a trill between these two notes, because the springs couldn't really get going in time. So we know that our ears have much less resonance persistence than these springs do. But let's listen to some more trills, or Helmholtz calls them shakes. They do get harder to distinguish the lower in pitch you go. So there must be different parts of the ear which are set in vibration by tones of different pitch and which receive the sensations of these tones. Otherwise, there would be no difference in how we perceive a high-pitched trill and a low-pitched trill. Now, Helmholtz does not definitively say which part of the ear is vibrating sympathetically to different pitches. But he does say that the basilar membrane is set up pretty well to do it. According to Saltire, there are about 4,500 outer arch fibers in the human cochlea. If we deduct 300 for the simple tones which lie beyond musical limits and cannot have their pitch perfectly apprehended, there remain 4,200 for the 7 octaves of musical instruments, that is 600 for every octave, 50 for every semitone, that is 1 for every 2 cents. Certainly quite enough to explain the power of distinguishing small parts of a semitone. Let's try and distinguish some small parts of a semitone. Let's start easy with 50 cents. Cakewalk. Let's try 25. All right, 10. Five. 3. If you want to test your ear on 2 cents or even 1 cent, go to sensationsoftone.com. And be sure to subscribe so you don't miss next week when we get to part 2 of the book on the interruptions of harmony, combinational tones and beats, consonants and dissonance. I'll see you then. Bye!